we're being asked to set up an integral in cylindrical coordinates that finds the volume that's above the cone but below the sphere. Cylindrical coordinates is just a fancy way of saying z, r, and theta. And in practice, what that usually means is we start the integral with z, and after we smush, we use r and theta. So let's just start. I'm going to draw the cone. That's just our normal cone, but a little bit steeper. And then we want to draw the hemisphere. It's going to come up like this. It's going to come over like this. It's going to hit just like that. And it looks like that. I want to start doing integrals. And almost always with cylindrical coordinates, we want to start with z. So I'm going to say, let's do dz. Now if I do dz first, I'm supposed to be drawing lines parallel to the z-axis. Well, the z-axis runs right dead center through here like this. So I just start drawing some lines like this. And you can see that each of those lines enters the region at the cone, and each of those lines leaves the region at the sphere. So what I need to know is what is z at the cone and what is z at the sphere. If I look at z equals 3 squared of x squared plus y squared, that's just z equals 3r. So I like that. If I look at the second piece here, I need to solve this for z, but I have to remember that it has to be in terms of r and theta. So I know, knowing that x squared plus y squared is r squared, I'll write r squared plus z squared equals 25 like that. I'll solve for z. I'll get plus or minus the square root of 25 minus r squared. We're only going to worry about the positive z because we're only looking at the top half of the hemisphere. And what do we have here? We have that z enters the region when z is 3r. Those lines leave the region when z is equal to the square root of 25 minus r squared. Now we know that the next part of the process is smushing. Now, what are we going to see when we smush? Well, what we're going to see is actually from above is the shadow of that intersection. So I do need to find that intersection. I'm just going to try to put it here in blue and hope I can make it work. What do I need to do? I'm going to solve my second equation for z squared. So z squared equals 25 minus r squared like that. I'm going to solve my second equation for z squared. Z squared, let's put it down here. Z squared is 9r squared like that. So this is going to be equal to 9r squared like that. Just making sure I did this right. I have 25 minus r squared equals 9r squared. It does look right. So I'm going to get 25 is equal to, it looks like 10r squared. And then r squared is going to be plus or minus the square root of what looks like 25 tenths. And I'm only using positive r's in this case, so I'm going to do that. So what I'm going to see is that r is equal to the square root of 25 tenths, and that's just a circle. So when we smush, we're smushing to this circle, where the radius of that circle is the square root of 25 tenths. Like this. 25 tenths, I think that's just 5 halves. So I'm going to go like that. And once we smush, we know what we're supposed to do. We're supposed to start drawing rays. It's going to look like that. Each of those rays enters the region at the origin when r is 0, so I put a little 0 there. Each of those rays leaves the region at the edge of the circle whose radius is the square root of 5 halves, so it's just going to leave at the square root of 5 halves like that. And we've now taken care of the r, and now we need to do d theta. And we just have to ask ourselves, as I was drawing all of those rays to fill the circle, what thetas was I using? I think we were using from 0 to 2 pi. And that's how you do a integral in cylindrical coordinates. You still have to draw it. We still have to draw lines. We still have to smush. But when we smush, we use r and theta instead of x and y.